Okay, this is gas laws part 2. We have related pressure and volume and temperature and volume, but we have yet to relate pressure and temperature. So this is Gay-Lussac's law. Joseph Gay-Lussac is this guy up here, and he found the relationship between these two. He found that the pressure of a given mass of gas varies directly with the Kelvin temperature when the volume remains constant. So just like with our whatchamacallit, popsicle stick, we know that when we covered up volume, pressure and temperature were directly related. Okay, and just a reminder that temperature must be in Kelvin. And here's a graph that shows you as temperature increases, pressure increases. Directly related. Okay, and here's a practice problem. It says solve the following. The pressure of a gas in a tank is 3.2 atm at 22.0 degrees Celsius. If the temperature rises to 60 degrees Celsius, what will be the gas pressure in the tank? So here we have pressure 1 and temperature 1. And if the temperature rises, it's going to be our T2, what will the gas pressure be in the tank? So we're looking for P2. So you simply just plug in, but before you plug in, you must convert the Celsius to Kelvin by adding 273 for both of them. And then we plug in. P1 is 3.2. T1 is now 295 in Kelvin. We do not know pressure 2. And then Kelvin here is 333 for temperature 2. So then we just do the math, solve it, and you get 3.61 atm. And we are in the right number of sig figs, so we are good to go right there. Now, we can combine Boyle's, Charles, and Gay-Lussac's all together. And it's called the combined gas law. So basically, we have the P1V1 and the P2V2 all over T1. So that line should actually be right there. And the combined gas law states that the relationship among pressure, volume, and temperature of a fixed amount of gas. And remember again that we must be in Kelvin. Here's just a sample problem. It says solve the following. A gas at 110 kilopascal, so we know that's pressure, so that's P1, and 30 degrees Celsius, so that's our temperature 1, fills a flexible container with an initial volume of 2 liters, so that's our V1. And then if the temperature is raised, so our T2 is now 80 degrees Celsius, and the pressure increases to 440, that's our new pressure, P2, what is the new volume? So our unknown is V2. So we'll take our combined gas law and plug that in after we convert to Kelvin for both of the temperatures. So we have P1 is 110, V1 is 2 liters, T1 is 303, and then P2 is 440, V2 is our unknown, and T2 is 353. Do all the math, and we get 0.582, which should be rounded to 2 sig figs, so it should be 0.58 liters. Good. Another law, can you believe it? The ideal gas law. In all the other gas laws, the relationships hold true for a fixed mass or given amount of a gas sample. Because pressure, volume, temperature, and the number of moles present are all interrelated, one equation is used to describe their relationship. And I think another chemistry teacher said PEVNERT is how she remembers it. But I honestly remember PV equals nRT from when I was in high school. So anyway, we have pressure, volume, the number of moles, and this is going to be a constant that's dependent upon the units of pressure. And then we have temperature that has to be in Kelvin again. So here's the different R values depending on the units for pressure. If pressure is mmHg or torr, it's going to be 62.4. If it is ATM, it's going to be 0.0821. And if it's kilopascal, it will be 8.31. So those are just going to be something you have to remember for now. Well, I mean, to remember which one to use. So here's an example. Solve the following. 44.01 grams of CO2 occupies a certain volume at standard temperature and pressure, which, if you'll remember, is 273 Kelvin and 1 atm. That's our standard temperature and pressure. It says find that volume. So we're going to use the PV equals NRT. And N is going to be the sample mass, which was given here, divided by the molar mass of CO2. So sample mass, 44.01, molar mass found on the periodic table, and we get 1 mole. So that will be our 1 right here. So then we just plug in standard pressure is 1 atm, V is our unknown. We got 1 mole. That's the R if our pressure is an atm, and there is our Kelvin value. Standard temperature. So then we solve and we get 22.4 liters. We should add a 0 on there because we are given 4 sig figs. All right, another practice problem. Find the molar mass of a gas that weighs 0.7155 grams and occupies a volume of 250 milliliters at standard temperature and pressure. So we're looking for molar mass. So now we're going to find the moles and go backwards to find the molar mass. So we'll plug in our pressure. We got standard temperature and pressure. So we got 1 atm. Volume is 250 milliliters, but we need it to be in liters. If you'll remember, for ideal gas law, we have to have volume in liters. N is our unknown. We've got pressure in atm again, so we're going to use that R value, and then the temperature is 273. When we solve for N, we get 0.011 moles, so we're going to take and divide that into the grams that we were given right here, and we get that the molar mass is 68.64. And you should be able to look on the periodic table and figure out which element it is, which gas. All right, last thing we need to discuss, Dalton's law of partial pressure. This just says the total pressure, if you have a mixture of gases, is going to be equal to the sum of each of those pressures. Pretty straightforward. So here we have a mixture of oxygen, carbon dioxide, and nitrogen, and they have a total pressure of 0.97 atm. So that's our pressure total. What is the partial pressure of oxygen if the partial pressure of CO2 is 0.7 and the partial pressure of nitrogen is 0.12? So basically our total is going to be equal to oxygen, or unknown, plus the 0.7 plus the 0.12. So we're just going to do the math, and the pressure of oxygen comes out to be 0.15 atm. And, oh, I'm sorry, that wasn't the last thing. That was the easiest thing, but that wasn't the last thing. Avogadro's principle is the last thing. And this is kind of going back to stoichiometry a little bit. It says that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. So the volume that 1 mole of gas occupies at standard temperature and pressure is always going to be this number, 22.4 liters per mole. So when we do stoichiometry and we're setting up our what goes on bottom, what goes on top, you can use this number for that. And here's an example. We start with 42.7 grams of CO. That is our given, so we're going to write that down. And then it wants to know, it's at standard temperature and pressure, what volume of nitrogen gas will be produced. So we've got our balanced equation right here. So we start with 42.7 grams of CO. The grams of CO is on the top, so grams of CO goes on the bottom. So we look to the periodic table to find our molar mass for 1 mole of CO. And then mole of CO goes on the bottom here. And we look at molar ratio. We've got 2 moles of CO and we want to go to nitrogen gas, which is N2, to 1 mole of N2. So those go right here. Then moles of N2 will go on the bottom here. And that's where we'll use that number from the last slide, the 22.4. That's how many liters are in any mole of a gas at standard temperature and pressure. So we get that 22.4. So now all of our units that we need to cancel will cancel, and will be in liters of nitrogen gas, which is our volume of nitrogen gas. So we have 42.7 times 22.4 divided by 28 divided by 2, and we get 17.1 liters of N2. Sorry, I went back to sig figs again. And that's it. That's our last slide, and I thank you guys for listening. Bye-bye.